Welcome to this peaceful journey through the cosmos. For the next 2 hours or so, we'll drift together through the vast expanse of space, exploring the wonders that fill our night sky. Let yourself relax, breathe deeply, and allow the majesty of the universe to wash over you. There's no need to concentrate intensely on every word. Simply let the information flow over you like a gentle stream, carrying you deeper into relaxation with each passing moment. If you drift into sleep, that's perfectly fine. The cosmos will continue its eternal dance, and these words will accompany you on your journey into rest. Above us, even on the clearest night, we can only see about 2,500 stars with our naked eyes. Yet this represents just the tiniest fraction of what exists. Our Milky Way galaxy alone contains between 100 and 400 billion stars, each one a sun in its own right, many with their own families of planets orbiting in the darkness. Think about that for a moment. 2,500 stars visible to us, out of hundreds of billions that exist in our galaxy alone. It's as if we're standing at the shore of an infinite ocean, seeing only the few grains of sand immediately at our feet, while millions of beaches stretch endlessly in all directions, each with countless grains we'll never see. And our galaxy is just one among trillions of others scattered throughout the observable universe, each containing their own billions or trillions of stars. The universe is so vast that light itself, traveling at 186,000 miles per second, takes billions of years to cross from one side of the observable universe to the other. As we begin, take a moment to imagine yourself floating weightlessly among the stars, free from the constraints of Earth, drifting peacefully through the infinite expanse of space and time. Feel the gentle pull of gravity release you. Feel yourself becoming lighter, lighter still, until you rise effortlessly into the dark velvet of space, surrounded by points of light that have been shining for millions of years, their ancient photons finally reaching you in this moment. Breathe in the vastness. Breathe out any tension you're holding. Let yourself become part of the cosmic flow. Let's start our journey with our closest celestial neighbor, the Moon. Hanging in our sky at an average distance of 238,855 miles, the Moon has captivated humanity since the dawn of our existence. It's the fifth largest moon in our solar system, and the largest relative to the size of its parent planet. In a sense, Earth and the Moon are almost a double planet system, locked in an eternal gravitational embrace. The Moon is gradually moving away from Earth at a rate of about 1.5 inches per year. This happens because of tidal interactions between our planet and its satellite. As the Moon's gravity raises tides on Earth, tides in our oceans, but also subtle tides in the solid rock of the Earth itself, friction slows Earth's rotation ever so slightly. This rotational energy isn't lost. It's transferred to the Moon, pushing it gradually into a higher orbit. In the distant future, billions of years from now, it will appear much smaller in our sky than it does today. The majestic full moon that has inspired poets and lovers throughout human history will become a smaller, more distant disk. When the Moon first formed about 4.5 billion years ago, it was much closer to Earth, perhaps only about 15,000 miles away compared to its current 250,000-mile distance. At that time, it would have appeared enormous in the sky, perhaps 15 times larger than we see it today. The tides would have been tremendous, and Earth's day was much shorter, perhaps only 5 or 6 hours long. Over billions of years, the Moon has gradually spiraled outward to its current position, and will continue to do so. The Moon's phases follow a precise 29.5-day cycle, known as a synodic month. From the delicate crescent of the new moon to the brilliant fullness and back again, this celestial dance has marked the passage of time for countless generations. Ancient peoples around the world based their calendars on these lunar cycles. The words month and Monday both derive from moon. Our ancestors looked to the moon to know when to plant crops, when to harvest, when to celebrate festivals and mark the passage of seasons. The phases occur because of the changing angle between the sun, moon, and earth. The moon doesn't produce its own light. What we see is sunlight reflecting off its surface, that ancient, dusty surface that has remained largely unchanged for billions of years. When the moon is between Earth and the sun, we see the side that isn't illuminated. This is the new moon, invisible in our sky. As the moon moves in its orbit, more of the illuminated side becomes visible to us, creating the waxing crescent, first quarter, waxing gibbous, and finally the full moon when the entire face is lit. Then the cycle reverses with the waning gibbous, last quarter, and waning crescent leading back to the new moon. The dark patches we see, which form the face many cultures have identified, the man in the moon, or the rabbit in the moon, are actually vast plains of solidified lava from volcanic eruptions that occurred over 3 billion years ago. These are called maria, the Latin word for seas, because early astronomers thought they might be oceans. They're the result of massive asteroid impacts that excavated huge basins, which later filled with lava from the moon's interior when it was still geologically active. The lighter-colored regions are the lunar highlands, the original crust of the moon, heavily cratered and ancient beyond our ability to truly comprehend. The same side of the moon always faces Earth due to a phenomenon called tidal locking. Early in the moon's history, Earth's gravity created tidal bulges in the moon itself. As the moon rotated, these bulges moved, but friction gradually slowed the moon's rotation until it matched its orbital period. Now the moon rotates once for each orbit around Earth, keeping the same face toward us always. This means there truly is a dark side of the moon, or more accurately, a far side, that remained unseen by human eyes until spacecraft photographed it in 1959. The far side of the moon is quite different from the near side. It has far fewer maria, those dark lava plains, and is much more heavily cratered. Scientists believe this is because the crust is thicker on the far side, making it harder for lava to reach the surface after impacts. The far side is also more rugged and mountainous, a terrain of ancient highlands that has remained essentially unchanged since the moon's formation. During a total lunar eclipse, the moon can appear blood red. This happens because Earth's atmosphere filters sunlight, allowing only red wavelengths to reach the moon's surface, painting it in shades of copper and crimson. If you were standing on the moon during a lunar eclipse, you would see Earth blocking out the sun, but you'd see a brilliant red ring around Earth. This is sunlight refracting through Earth's atmosphere, every sunrise and sunset happening on Earth at that moment, all that red light being bent around our planet to illuminate the lunar surface. From our perspective on Earth, we see this light reflected back, turning our silver moon into an eerie red sphere hanging in the night sky. The moon's surface is covered in craters, the scars of billions of years of asteroid and meteor impacts. Without an atmosphere to burn up incoming space debris, every collision leaves its mark permanently etched into the lunar landscape. Some of these craters are enormous. The South Pole Aitken Basin on the far side is over 1,600 miles in diameter and more than 8 miles deep, one of the largest impact craters in the entire solar system. Every crater tells a story of a violent impact, some occurring billions of years ago when the solar system was young and debris was far more common than it is today. The lunar surface is covered in a layer of fine dust called regolith, created by billions of years of meteorite impacts grinding rock into powder. This dust is incredibly fine and sharp, not rounded by water and wind like sand on Earth. When the Apollo astronauts walked on the moon, the dust clung to everything, got into equipment, and was nearly impossible to brush off. It smells like spent gunpowder, they reported, the result of its chemical composition and the fact that it's constantly being exposed to solar radiation in the absence of an atmosphere. The moon has moonquakes similar to earthquakes, caused by tidal forces from Earth's gravity and the cooling and contracting of the moon's interior. These can last for over half an hour, much longer than earthquakes on our planet. Seismometers left by Apollo astronauts detected these moonquakes and found that the moon rings like a bell when struck, because its interior structure is different from Earth's. While Earth has a molten outer core that dampens seismic waves, the moon's interior is more rigid, allowing vibrations to continue for much longer. The moon's influence on Earth extends far beyond the romantic tides of poetry. The moon stabilizes Earth's axial tilt, which is crucial for our climate stability. Without the moon, Earth's tilt would vary chaotically over millions of years, causing wild swings in climate that might have prevented the development of complex life. The moon may have been essential to the emergence of life on Earth, providing stable conditions for billions of years of evolution. Breathe deeply as you imagine standing on that silent, airless surface, looking back at Earth hanging in the black sky, a blue and white marble of unimaginable beauty suspended in the void. The Earth doesn't rise or set from the moon's near side. It hangs in essentially the same spot in the sky always, slowly rotating to show different continents and oceans as it spins on its axis. The stars never twinkle on the moon. Without an atmosphere, they shine steadily, constant points of light in the absolute black of space. The silence is complete, total, profound. No wind, no sound, no atmosphere to carry vibrations. Just you, the ancient dust beneath your feet, and the cosmos stretching infinitely in all directions. The planets, wanderers of the solar system. The word planet comes from the Greek word planets, meaning wanderer. Ancient astronomers noticed that while most stars remained fixed in their positions relative to each other, certain bright objects moved against this stellar backdrop, night after night, wandering through the constellations in their endless orbital dance around the sun. These wanderers fascinated ancient peoples, who attributed divine significance to them and named them after their gods. Today we know them as the planets of our solar system, each one a unique world with its own characteristics, mysteries, and wonders. Mercury, the swift messenger. Mercury, the smallest planet in our solar system and closest to the Sun, has the most eccentric orbit of all the planets. Its orbit is so elliptical that its distance from the Sun varies from 29 million miles at its closest approach to 43 million miles at its farthest point. This means the intensity of sunlight Mercury receives varies dramatically over the course of its orbit. Despite being scorched by solar radiation during its day, with surface temperatures reaching 800 degrees Fahrenheit, hot enough to melt lead and tin, Mercury actually has water ice and permanently shadowed craters at its poles. These craters are deep enough that sunlight never reaches their floors, and in these eternal shadows, temperatures can drop to minus 280 degrees Fahrenheit. Ice has remained frozen there for perhaps billions of years, deposits left by ancient comet impacts, preserved in darkness while the surrounding landscape bakes under the relentless sun. A single sidereal day on Mercury, defined as one full rotation on its axis, takes 59 Earth days. But a year on Mercury, one complete orbit around the Sun, takes just 88 Earth days. This creates a peculiar situation, because Mercury's rotation and orbit are in a 3-to-2 resonance. A full solar day on Mercury, measured from sunrise to sunrise, actually takes 176 Earth days, exactly 2 Mercurian years. This means that if you stood on Mercury's surface, you would see the sun rise, slowly traverse the sky for 1 Mercurian year, set, then rise again briefly before setting once more, then rise and traverse the sky for another Mercurian year before finally setting. All this comprising a single day-night cycle. The sun would appear to stop and reverse direction in the sky at certain times due to the interplay between the planet's rotation and its orbital motion. It's a dance of cosmic mechanics that creates one of the strangest day-night cycles in the solar system. Mercury has no moons, no atmosphere to speak of, just the thinnest exosphere of atoms knocked off its surface by the solar wind. The sky is always black, even at midday, because there's no atmosphere to scatter light. Standing on Mercury, you'd see the sun as a brilliant disk 3 times larger than it appears from Earth, blazing in a star-filled black sky. The surface is heavily cratered, much like the moon, with ancient impact basins and vast smooth plains. The largest crater, Caloris Basin, is over 950 miles in diameter, created by an impact so violent it sent shock waves through the entire planet, creating disrupted terrain on the exact opposite side of Mercury. Venus, the veiled world. Venus shines brilliantly in our sky, often the first star visible after sunset or before sunrise. The ancient Romans named it after their goddess of beauty and love, and it's easy to see why when you witness its radiant glow. Venus can be bright enough to cast shadows on Earth on a dark night, and at its brightest, it can even be seen during the daytime if you know where to look. Yet beneath this beautiful exterior lies one of the most hellish environments in the solar system. Venus rotates backwards compared to most planets in our solar system, spinning from east to west rather than west to east. We call this retrograde rotation. Scientists believe this may have resulted from a massive collision early in the planet's history. Perhaps Venus was struck by a large object that literally knocked it into a backward spin. Or it could be the result of tidal effects from the Sun on Venus's thick atmosphere. Whatever the cause, Venus now spins slowly backwards, taking 243 Earth days to complete one rotation, longer than its orbital period of 225 Earth days. This means a day on Venus is longer than its year, and the Sun rises in the west and sets in the east. The atmospheric pressure on Venus's surface is 92 times greater than Earth's, equivalent to being 3,000 feet underwater in Earth's oceans. The thick atmosphere of carbon dioxide creates a runaway greenhouse effect, making Venus the hottest planet in our solar system at about 900 degrees Fahrenheit, even hotter than Mercury despite being twice as far from the Sun. The thick clouds of sulfuric acid reflect most sunlight, but the greenhouse effect traps enough heat to maintain these infernal temperatures constantly, with virtually no difference between day and night, or between the equator and poles. Venus's clouds race around the planet in just 4 Earth days, driven by superrotating winds in the upper atmosphere. Lightning flashes constantly in these clouds. The atmospheric pressure and heat have destroyed every spacecraft that has landed on Venus within hours of arrival. Russian Venera probes that landed on Venus in the 1970s and 1980s sent back a few images and data before succumbing to the extreme conditions. They showed a rocky landscape lit by an orange glow filtering through the thick atmosphere, a world where it's hot enough to melt lead and the air would crush and corrode any visitor. Venus may have once been much more Earth-like, with liquid water oceans on its surface. Some scientists believe Venus maintained habitable conditions for perhaps 2 billion years after its formation. But at some point, a runaway greenhouse effect took hold. As temperatures rose, oceans evaporated, water vapor, itself a greenhouse gas, trapped more heat, leading to more evaporation and a self-reinforcing cycle that eventually boiled away the oceans entirely and left Venus as the oven world we see today. Solar radiation broke apart the water molecules in the upper atmosphere, and the hydrogen escaped to space while the oxygen reacted with rocks on the surface. Venus lost its water forever. Some scientists suggest that Earth could suffer a similar fate billions of years from now as the Sun grows brighter, though we have time, billions of years, before that becomes a concern. Mars, the red planet. Mars appears red because its surface is rich in iron oxide, essentially rust. This rust covers ancient rocks that tell the story of a world that once had flowing water and a thicker atmosphere. The red color comes from the oxidation of iron-rich minerals in the Martian soil, giving the planet the appearance that led ancient peoples to associate it with blood and war, naming it after the Roman god of warfare. Mars has the largest volcano in the entire solar system, Olympus Mons, which stands about 16 miles high, nearly 3 times the height of Mount Everest, and is roughly 370 miles in diameter at its base. That's approximately the size of Arizona. Olympus Mons is a shield volcano, similar to the volcanoes in Hawaii, built up by countless eruptions of lava over billions of years. It's so vast that if you stood on its surface, you couldn't see the edges, they would be beyond the horizon. And you couldn't see the top from the base either. It slopes so gradually that you might not even realize you were climbing a mountain until you noticed the atmospheric pressure dropping as you ascended. Mars has other geological wonders too. Valles Marineris is a system of canyons that stretches over 2,500 miles across Mars's surface, up to 4 miles deep and 125 miles wide in places. If it were on Earth, it would stretch from New York to Los Angeles. This makes the Grand Canyon look like a small scratch on the surface by comparison. Scientists aren't sure exactly how Valles Marineris formed, though it likely began as a crack created when the Tharsis volcanic region bulged upward billions of years ago, then was widened by water erosion, landslides, and other geological processes. A day on Mars is remarkably similar to Earth's, lasting 24 hours and 37 minutes. This similarity makes Mars feel, in some ways, like a distant cousin to our own world. Mars also has seasons like Earth, because its axis is tilted at about 25 degrees, similar to Earth's 23.5-degree tilt. However, Martian seasons last about twice as long because Mars takes 687 Earth days to orbit the Sun. Mars also has polar ice caps that grow and shrink with the seasons, made of water ice and carbon dioxide ice. The evidence suggests Mars once had rivers, lakes, and perhaps even oceans. Ancient river valleys, sedimentary rock layers, and minerals that form only in liquid water all point to a warmer, wetter past. Mars was likely much more Earth-like billions of years ago, with a thicker atmosphere kept warm by greenhouse gases. But Mars is smaller than Earth, and its interior cooled more quickly. As the interior cooled, the magnetic field that had protected the atmosphere shut down. Without this magnetic shield, the solar wind gradually stripped away much of the atmosphere over hundreds of millions of years. As the atmosphere thinned, temperatures dropped, and liquid water could no longer exist on the surface. What water remained either froze into the polar ice caps and underground ice deposits, or was lost to space. Mars has two small moons, Phobos and Deimos, named after the Greek gods of fear and panic who accompanied Ares, Mars, into battle. These moons are irregularly shaped and probably captured asteroids rather than moons that formed alongside Mars. Phobos, the larger of the two, is gradually spiraling inward and will eventually be torn apart by Mars's gravity, possibly forming a ring system around the planet. This won't happen for another 50 million years or so. Mars has time yet before losing its companion. Despite being cold and dry today, Mars remains the most potentially habitable planet in our solar system besides Earth. Its day length, seasonal cycle, availability of water ice, and relatively moderate conditions compared to Venus make it a prime target for future human exploration. Perhaps someday humans will stand on Mars, looking up at the salmon-pink sky during the day or the twin moons at night, making the red planet a second home for humanity. Jupiter, the giant. Jupiter is truly colossal. This gas giant is so large that all the other planets in our solar system could fit inside it with room to spare. Jupiter's volume is over 1,300 times that of Earth, though its mass is only about 318 times Earth's mass because Jupiter is made mostly of hydrogen and helium, the lightest elements, in gaseous and liquid forms. Jupiter contains more than twice the mass of all the other planets combined. If Jupiter had been about 80 times more massive, it would have ignited nuclear fusion in its core and become a star rather than a planet. In some alternate solar system, Jupiter might have been the second sun, making ours a binary star system. Jupiter's Great Red Spot is a storm that has been raging for at least 350 years, possibly much longer. We've been observing it since the 1600s, but it may have been raging for thousands of years before telescopes were invented. This anticyclonic storm is so large that 2 or 3 Earths could fit inside it, though it has been shrinking over the past century for reasons scientists don't fully understand. It may eventually disappear or it may persist for centuries more. The winds in the Great Red Spot reach speeds of 270 miles per hour, and it rotates once every 6 days. The storm's red color comes from complex chemical reactions in Jupiter's atmosphere, possibly involving phosphorus or sulfur compounds brought up from deeper layers. Jupiter's atmosphere is a dynamic, turbulent place with multiple storm systems, zones of ascending and descending gas creating the characteristic banded appearance, and winds reaching 400 miles per hour. The atmosphere is made primarily of hydrogen and helium, with traces of methane, ammonia, water vapor, and other compounds. Below the visible cloud tops, the pressure and temperature increase dramatically. Descending into Jupiter, you would pass through different cloud layers. Ammonia ice clouds, then ammonium hydrosulfide clouds, then water ice clouds deeper still. Eventually the pressure would become so great that the hydrogen itself would be compressed into a liquid form. Deeper still, the pressure would be so immense that the hydrogen would take on metallic properties, conducting electricity like a metal. At Jupiter's core there may be a solid core of heavy elements, but we're not certain. The pressure there would be tens of millions of times Earth's atmospheric pressure, and the temperature would be around 50,000 degrees Fahrenheit, hotter than the surface of the Sun. Jupiter has at least 95 known moons, and more are being discovered regularly as our telescopes improve. Among these, the 4 large Galilean moons discovered by Galileo in 1610, Io, Europa, Ganymede, and Callisto, are worlds unto themselves. Io is the most volcanically active body in the solar system, with hundreds of volcanoes erupting constantly, spewing sulfur compounds that give Io its yellow and orange colors. This volcanic activity is driven by tidal heating. As Io orbits Jupiter, the immense gravitational pull flexes and squeezes the moon, generating friction and heat in its interior. Europa is particularly intriguing to scientists searching for life beyond Earth. This moon is covered in a shell of water ice that's crisscrossed with cracks and ridges, and beneath this ice is believed to be a vast ocean of liquid water, perhaps 40 to 100 miles deep, more water than all of Earth's oceans combined. This ocean is kept liquid by tidal heating from Jupiter's gravity, similar to Io but less extreme. Where there's liquid water, there's potentially life, and Europa has become one of the primary targets in the search for extraterrestrial life. Future missions may drill through the ice or look for plumes of water vapor erupting from the surface. Ganymede is the largest moon in the solar system, even larger than the planet Mercury, and is the only moon known to have its own magnetic field. Callisto is heavily cratered, its surface representing one of the oldest, most heavily cratered surfaces in the solar system, a record of impacts stretching back billions of years. Jupiter's powerful gravitational field acts as a cosmic vacuum cleaner, attracting comets and asteroids that might otherwise threaten the inner solar system, including Earth. The most dramatic demonstration of this was in 1994, when comet Shoemaker-Levy 9 broke apart and collided with Jupiter in a series of spectacular impacts that left dark scars in Jupiter's atmosphere visible even through small telescopes from Earth. Each impact released energy equivalent to millions of nuclear weapons. In this way, Jupiter serves as a protective guardian for our planet, its gravity deflecting or capturing objects that might otherwise pose a threat to Earth. Some scientists believe that without Jupiter's presence in the outer solar system, Earth might have experienced far more devastating impacts, potentially preventing the evolution of complex life. Jupiter also has faint rings, though nothing like Saturn's magnificent display. These rings are made of dust particles knocked off Jupiter's small inner moons by meteorite impacts. They're difficult to see but were discovered by the Voyager spacecraft in 1979. Saturn, the ring jewel. Perhaps no planet captures the imagination quite like Saturn with its magnificent ring system. Even through a small telescope, Saturn is breathtaking, a golden orb girdled by rings that seem impossible, too perfect to be real, like an artist's rendering rather than an actual world. Saturn's rings, while spanning over 280,000 kilometers in diameter, more than 170,000 miles, wide enough to stretch 2/3 of the way from Earth to the Moon, are incredibly thin. In some places they're only about 30 feet thick. If you had a model of Saturn's rings the size of a football field, they would be thinner than a piece of paper. Despite their immense extent, if you gathered all the ring material together, it would form a moon only about 100 miles in diameter. The rings are incredibly flat, kept in a single plane by Saturn's gravity and the gravitational interactions of the countless particles that make them up. Saturn's rings are made primarily of countless chunks of water ice, ranging in size from tiny grains smaller than a grain of sand to house-sized boulders. These particles orbit Saturn in an intricate dance, shepherded by small moons that keep the rings in their graceful patterns. Some of these shepherd moons orbit within the rings themselves, clearing gaps with their gravity. The Cassini division, a large gap visible even through small telescopes, is maintained by the gravitational influence of Saturn's moon Mimas. Particles in that region are in orbital resonance with Mimas and get pulled out of the gap. The origin of Saturn's rings is still debated. They could be the remnants of a moon that was torn apart by Saturn's gravity when it wandered too close, or they could be material that was prevented from coalescing into a moon during the solar system's formation. The rings may be ancient, dating back billions of years, or they could be relatively young, perhaps only 100 million years old. Recent data from the Cassini spacecraft suggests the rings may indeed be young, perhaps formed when a comet or small moon broke apart near Saturn in the relatively recent past. Saturn itself is the least dense planet in our solar system. Its average density is less than water. If you could find an ocean large enough, Saturn would float in it. This low density occurs because Saturn, like Jupiter, is made primarily of hydrogen and helium in gaseous and liquid forms, with only a small rocky core. Saturn's rapid rotation, a day on Saturn lasts only about 10.5 hours, causes it to bulge noticeably at the equator, giving it an oblate shape. Saturn has at least 145 known moons, ranging from tiny moonlets to Titan, the second largest moon in the solar system. Titan is larger than the planet Mercury and is the only moon in the solar system with a substantial atmosphere. In fact, its atmosphere is thicker than Earth's. Titan's atmosphere is mostly nitrogen like Earth's, but with methane and other hydrocarbons that create a thick orange haze. On Titan's surface, it's cold enough that water ice is as hard as rock, and methane and ethane exist as liquids, forming lakes, rivers, and rain. Titan has a complete hydrological cycle, but with liquid methane instead of water. Titan's lakes are vast, some larger than the Great Lakes of North America, filled with liquid methane and ethane. When it rains on Titan, it rains gasoline-like hydrocarbons. Wind blows across the landscape, creating dunes of hydrocarbon particles. In many ways, Titan is Earth-like in its surface processes, just operating at temperatures around -290 degrees Fahrenheit. Enceladus, another of Saturn's moons, is even more intriguing for the search for life. This small, icy moon has geysers of water vapor erupting from cracks near its south pole, shooting plumes of ice particles and vapor hundreds of miles into space. The Cassini spacecraft flew through these plumes and detected not just water but also organic compounds and salts, suggesting that beneath Enceladus's icy crust lies a global ocean in contact with a rocky core, conditions that might support life. Saturn's atmospheric features include storms and high-speed winds, though they're less prominent than Jupiter's due to Saturn's thick hazy atmosphere. Occasionally, massive storms erupt in Saturn's atmosphere, great white spots that can grow to encircle the entire planet. These megastorms occur roughly every 30 years, once per Saturnian year, and can last for months, with winds reaching 1,000 miles per hour. Uranus, the tilted world. Uranus rotates on its side, tilted at an angle of 98 degrees relative to its orbital plane. This means that for part of its 84-year orbit around the Sun, one pole points almost directly at the Sun, giving it the most extreme seasons in the solar system. Imagine a season lasting 21 Earth years, during which the Sun never sets at one pole and never rises at the other. Then, over the course of the next 21 years, the Sun gradually sets at that pole as Uranus moves along its orbit, leading to 21 years where both hemispheres experience day and night, followed by 21 years where the opposite pole faces the sun continuously. It's a bizarre seasonal cycle unlike anything on Earth. Scientists believe Uranus was knocked on its side by a massive collision early in the solar system's history. Perhaps it was struck by an Earth-sized object that literally knocked it over. This collision may have also contributed to Uranus's relatively low internal heat output. Unlike Jupiter and Saturn, which radiate more heat than they receive from the Sun, Uranus radiates very little internal heat, suggesting something happened to its internal structure. The impact that tipped Uranus over may have caused it to lose much of its primordial heat. Uranus has a pale blue-green color due to methane in its atmosphere, which absorbs red light and reflects blue and green wavelengths back into space. Beneath the visible clouds, Uranus is thought to have a strange interior structure. Below the hydrogen and helium atmosphere lies a thick mantle of water, methane, and ammonia ices under enormous pressure. Not ice as we know it, but a hot, dense fluid sometimes called an ice giant interior. At the center may be a rocky core. The pressure in this mantle is so great that scientists think carbon could be compressed into diamonds, which would then rain down toward the core. Imagine that, a world where it rains diamonds. Uranus has a faint ring system discovered in 1977, and at least 27 known moons. Most of these moons are named after characters from the works of William Shakespeare and Alexander Pope, a unique naming convention among planetary moons. The 5 largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are varied worlds. Miranda is particularly strange, with a surface that looks like a patchwork of different terrains jumbled together, suggesting it may have been shattered by an impact and reassembled. Or perhaps intense tidal heating caused some parts of Miranda to resurface while others remained ancient and cratered. Uranus was the first planet discovered with a telescope, found by William Herschel in 1781. Before this, only the 5 planets visible to the naked eye, Mercury, Venus, Mars, Jupiter, and Saturn, were known. Uranus's discovery doubled the known size of the solar system overnight and sparked searches for additional planets, eventually leading to the discovery of Neptune. Neptune, the blue giant. Neptune, the 8th and farthest planet from the Sun in our solar system, is a world of deep blue and fierce storms. It has the strongest winds measured in the solar system, with speeds reaching up to 1,200 miles per hour, faster than the speed of sound on Earth. These supersonic winds howl around Neptune constantly, driven by internal heat and the planet's rapid rotation. Despite receiving only a tiny fraction of the sunlight that Earth receives, about 900 times less, Neptune radiates more than twice the energy it receives from the Sun, suggesting powerful internal heat sources drive its dynamic atmosphere. Neptune takes 165 Earth years to complete one orbit around the Sun. It was discovered in 1846, and completed its first full orbit since discovery only in 2011. In that sense, Neptune returned to its position of discovery for the first time in 2011. It has been observed for barely more than one Neptunian year. Neptune returned to the exact position in the sky where it was first observed, a milestone in planetary astronomy. Neptune's blue color is even more vivid than Uranus's and is also caused by methane in its atmosphere absorbing red light. But Neptune's color is a richer, darker blue, possibly due to an unknown component in its atmosphere that contributes additional blue absorption. The atmosphere is primarily hydrogen and helium, with methane and traces of other hydrocarbons. Neptune has dramatic weather features, including storms that come and go over periods of years. When Voyager 2 flew past Neptune in 1989, it observed a great dark spot similar to Jupiter's Great Red Spot, an enormous anticyclonic storm system. But when the Hubble Space Telescope observed Neptune a few years later, the Great Dark Spot had disappeared, replaced by different storms in other parts of the planet. Neptune's weather is dynamic and changing, with storms forming and dissipating more quickly than on Jupiter or Saturn. Neptune has 16 known moons, the largest of which is Triton. Triton is unusual because it orbits Neptune in a retrograde direction, backwards compared to Neptune's rotation. This suggests Triton wasn't formed alongside Neptune but was captured from the Kuiper Belt, the region of icy bodies beyond Neptune's orbit. Triton is geologically active, with nitrogen geysers erupting from its surface, ejecting material that falls back as snow. Triton has a thin atmosphere of nitrogen and is one of the coldest objects in the solar system, with surface temperatures around -391 degrees Fahrenheit. Because of Triton's retrograde orbit, tidal forces are gradually slowing it down, causing it to spiral slowly inward toward Neptune. In tens of millions of years, Triton will pass within Neptune's Roche limit, the distance at which Neptune's tidal forces will overcome Triton's self-gravity, and Triton will be torn apart, forming a spectacular ring system around Neptune that could rival or exceed Saturn's rings in magnificence. Neptune also has a faint ring system discovered in the 1980s. These rings are dark and contain some peculiar clumps of material called arcs, whose stability remains something of a mystery. Small shepherd moons may help maintain these arcs, but the full explanation isn't yet clear. Let your mind drift peacefully across these distant worlds, each one a unique expression of the physical forces that shape our universe. From the scorched surface of Mercury to the supersonic winds of Neptune, each planet tells part of the story of how our solar system formed 4.6 billion years ago from a rotating cloud of gas and dust. Each is a laboratory where we can observe physics at work under conditions utterly unlike anything on Earth. The stars, ancient furnaces of creation. Every star you see in the night sky is a massive nuclear reactor, fusing hydrogen into helium in its core, releasing tremendous amounts of energy in the process. This energy, in the form of light and heat, travels across the vastness of space to reach our eyes. Stars are the fundamental building blocks of galaxies, the creators of heavy elements, the sources of light and warmth that make life possible on planets fortunate enough to orbit at the right distance. The nuclear fusion happening in a star's core is the same process that powers hydrogen bombs, but in stars it's controlled by the immense gravitational pressure of the star's own mass. In the core of a star like our Sun, temperatures reach about 27 million degrees Fahrenheit, and the pressure is about 250 billion times Earth's atmospheric pressure. Under these extreme conditions, hydrogen nuclei, which normally repel each other due to their positive electric charges, are forced close enough together that the strong nuclear force overcomes the electromagnetic repulsion, and the nuclei fuse together, forming helium and releasing energy in the process. This energy doesn't reach the star's surface immediately. It can take hundreds of thousands or even millions of years for energy created in the core to work its way to the surface, being absorbed and re-emitted countless times by atoms in the star's interior. By the time this energy finally escapes into space as starlight, it has been on a long journey from the core through the stellar interior. The light from the stars we see tonight began its journey years, decades, centuries, or even millennia ago. When you look at the stars, you're literally looking back in time. Light travels at 186,000 miles per second, fast enough to circle Earth more than 7 times in a single second. Yet even at this incredible speed, the distances between stars are so vast that light takes years to cross them. The nearest star system to Earth, Alpha Centauri, is 4.37 light-years away, meaning the light you see from it tonight actually left that star in 2021. The North Star, Polaris, is about 323 light-years away, meaning the light you see from it tonight actually left that star in the year 1702, before the United States existed, when Isaac Newton was still alive. Some stars visible to the naked eye are thousands of light-years distant. Their light left during the age of the ancient Egyptians or the early Bronze Age, traveled through the emptiness of space for all those centuries, and arrives at your eye in this moment, a photon that has journeyed through time itself. Stars come in an incredible range of sizes and temperatures. The smallest stars, red dwarfs, can be as small as 1/10 the mass of our sun and burn their fuel so slowly that they could shine for trillions of years, longer than the current age of the universe. In fact, no red dwarf has ever died because the universe isn't old enough yet for even the first red dwarfs to have exhausted their fuel. They'll continue shining long after stars like our sun have burned out and died. The largest known stars, hypergiants like Uy or Stephenson 2-18, are so enormous that if placed at the center of our solar system, their surface would extend beyond the orbit of Jupiter, possibly even as far as Saturn. If the Sun were replaced by Uy, Mercury, Venus, Earth, and Mars would all be inside the star itself, vaporized instantly. These enormous stars are rare and short-lived. They burn through their nuclear fuel rapidly and may only last a few million years before exploding as supernovae. Stars are not eternal. They are born from collapsing clouds of gas and dust in nebulae, live for millions to trillions of years depending on their size, and eventually die in various ways, some fading quietly, others exploding in spectacular supernovae. The life cycle of a star is a story of nuclear physics, gravity, and time. Stars form when regions of gas and dust clouds become dense enough that their self-gravity causes them to collapse. As the cloud collapses, it heats up due to compression. Eventually, if the temperature and pressure in the core become high enough, nuclear fusion ignites and a star is born. The surrounding cloud of gas and dust may form a disk around the new star, and planets can form from this disk. This is how our solar system and presumably many others came into being. The color of a star indicates its temperature. Blue and white stars are the hottest, with surface temperatures exceeding 18,000 degrees Fahrenheit. These are massive, luminous stars that burn through their fuel quickly. Yellow stars like our sun are medium temperature, around 10,000 degrees Fahrenheit at the surface. Red stars are the coolest, though cool is relative. They still have surface temperatures of 5,400 degrees Fahrenheit or more. This color-temperature relationship allows astronomers to determine a star's surface temperature just by observing its color. Our own sun is a fairly average star, a yellow dwarf classified as a G-type main sequence star, about halfway through its 10 billion-year lifespan. It has been shining steadily for 4.6 billion years and will continue to do so for another 5 billion years or so before entering its final stages of stellar evolution. When the sun exhausts the hydrogen in its core, it will begin fusing helium into heavier elements, and its outer layers will expand dramatically, turning it into a red giant so large it may engulf Mercury, Venus, and possibly even Earth. Eventually, it will shed these outer layers, creating a planetary nebula, and the core will collapse into a white dwarf, a dense, Earth-sized ember that will slowly cool over trillions of years. The sun converts about 600 million tons of hydrogen into helium every single second through nuclear fusion. In the process, about 4 million tons of matter is converted into pure energy according to Einstein's famous equation, E=mc². This means the sun is literally losing mass as it shines, converting some of its substance into the light and heat that warm our world. Over its lifetime, the sun will have converted about 100 Earth masses worth of hydrogen into helium and energy. Some stars exist in binary or multiple star systems, orbiting each other in an eternal gravitational dance. In fact, most stars in our galaxy are part of multiple star systems rather than single stars like our sun. Binary stars can be close together, orbiting each other in hours or days, or widely separated, taking centuries or millennia to complete an orbit. Some binary stars are so close that they transfer material between them, with gas from one star flowing to its companion in a stellar embrace. If you lived on a planet orbiting a binary star, you would indeed witness double sunsets like those imagined in science fiction, with two suns in your sky at once, casting double shadows and creating complex patterns of day and night depending on your planet's orbital configuration. When massive stars, those at least 8 times the mass of our Sun, exhaust their nuclear fuel. They can no longer generate enough pressure to support themselves against their own gravity, and they collapse catastrophically. The core collapses in less than a second, and then rebounds in an explosion of unimaginable violence. A supernova. For a brief time, a supernova can outshine an entire galaxy containing hundreds of billions of stars. A single supernova releases more energy in a few weeks than our Sun will produce in its entire 10 billion-year lifetime. Supernovae are essential to the universe's evolution and to our own existence. The heavy elements that make up planets and life itself, carbon, oxygen, nitrogen, iron, gold, uranium, were all forged in the cores of massive stars through nuclear fusion, and then scattered into space by supernova explosions. The atoms in your body, the oxygen you breathe, the calcium in your bones, the iron in your blood, all were created inside stars that lived and died billions of years ago before our solar system even existed. When a massive star explodes, it enriches the interstellar medium with these heavy elements. When new stars and planetary systems form from this enriched material, they incorporate these elements. The first stars in the universe, formed from the primordial hydrogen and helium created in the Big Bang, had no heavy elements at all. No carbon, no oxygen, no iron. These elements had to be created in the first generation of stars and dispersed by their deaths before rocky planets and life as we know it could exist. We are, quite literally, made of stardust. The atoms that make up your body are ancient, formed in stellar furnaces billions of years ago, dispersed through space, eventually coalescing to form our solar system, Earth, and ultimately you. The stars in our night sky belong to various constellations, patterns that humans have identified and named throughout history. Orion the Hunter, with his distinctive belt of 3 stars and his sword hanging below. Ursa Major the Great Bear, containing the Big Dipper, which has guided travelers and inspired storytellers for millennia. Scorpius the Scorpion, with its curving tail and bright red heart marked by the star Antares. These patterns have served as celestial maps and inspired countless stories across cultures around the world. Different cultures have identified different patterns and told different stories about the same stars. What ancient Greeks saw as a great bear, some Native American tribes saw as a great bear being hunted. What Europeans called Orion, Egyptian cultures associated with Osiris. The stars themselves don't change, but the stories we tell about them reflect our diverse human cultures and our universal need to find meaning and pattern in the cosmos. The stars and constellations aren't actually close to each other in space. They simply appear near each other from our perspective on Earth. In reality, they may be hundreds or thousands of light years apart from each other, scattered through 3-dimensional space at vastly different distances from us. If you could somehow travel to another star system and look back, Earth's constellations would look completely different, scrambled into new patterns by the changed perspective. The stars move too, though so slowly that their positions relative to each other appear fixed over human timescales. Each star orbits around the center of the Milky Way galaxy, and some stars move through space more rapidly than others. Over tens of thousands of years, the constellations gradually change shape as the stars drift relative to each other. The Big Dipper of today will look noticeably different 50,000 years from now, its familiar ladle shape distorted by the individual motions of its component stars. Imagine floating among these stellar furnaces, feeling their ancient light wash over you, connecting you to the deep history of the cosmos itself. You are bathed in starlight that has traveled for years, centuries, or millennia to reach you. Every photon that enters your eye connects you across space and time to a distant stellar furnace, a nuclear reactor floating in the depths of space. You are looking at the universe's past, seeing things as they were, not as they are now. This is the strange magic of starlight and the vast distances between stars. Nebulae, clouds of creation and destruction. Nebulae are among the most beautiful structures in the universe, vast clouds of gas and dust floating in the space between stars, measured in light years across, containing the mass of thousands or millions of suns. The word nebula comes from the Latin word for cloud, and these cosmic clouds come in several varieties, each with its own story to tell about stellar life and death. Emission nebulae glow with their own light, energized by nearby hot, young stars. The intense ultraviolet radiation from these stars strips electrons from hydrogen atoms in the nebula, ionizing the gas. When electrons recombine with hydrogen nuclei, they emit light at characteristic wavelengths, particularly the red light of hydrogen alpha emission. This is why many nebulae appear red or pink in photographs. Though our eyes are often not sensitive enough to see these colors visually, long-exposure photographs reveal their spectacular hues. The famous Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is a stellar nursery where new stars are being born at this very moment. Located about 1,344 light-years from Earth, it's one of the brightest nebulae visible from Earth and one of the most studied objects in the night sky. The Orion Nebula is relatively close by cosmic standards, and its orientation allows us to peer into its depths, watching the process of star formation as it unfolds. Within the Orion Nebula, dense cores of gas and dust are collapsing under their own gravity, heating up as they contract. Some of these protostars are already hot enough to shine in infrared light, though they haven't yet ignited nuclear fusion. Around these protostars, disks of material are forming, protoplanetary disks where planets will eventually coalesce. We're witnessing the birth of new solar systems, watching a process that our own solar system underwent 4.6 billion years ago. The pillars of creation, photographed by the Hubble Space Telescope in the Eagle Nebula, have become one of the most iconic astronomical images ever taken. These are towering columns of gas and dust where stars are forming, sculpted by intense radiation and stellar winds from nearby young stars. These pillars are so large that they measure about 4 to 5 light-years in length, nearly the distance from our Sun to Proxima Centauri, the nearest star. If you could fly at the speed of light from the bottom of one pillar to the top, it would take 4 years. Within these pillars, dense clumps of gas called EGGs, evaporating gaseous globules, are collapsing to form new stars. The radiation from nearby hot stars is gradually eroding the pillars, but also compressing their denser regions, triggering star formation even as the pillars are destroyed. It's a race between creation and destruction, with new stars being born even as their natal clouds are torn apart by the radiation from previous generations of stars. Interestingly, the pillars of creation as we see them today may no longer exist. They're about 7,000 light-years away, so we're seeing them as they appeared 7,000 years ago. Infrared observations suggest a nearby supernova may have occurred about 6,000 years ago, and the blast wave from that explosion may have already destroyed the pillars. But we won't know for another 1,000 years, when the light showing their destruction finally reaches Earth. For now, in our sky, the pillars of creation still stand tall, monuments to stellar birth captured in a moment frozen in time. Reflection nebulae don't emit their own light but instead reflect the light of nearby stars. They appear blue because blue light scatters more efficiently through the dust particles that make up the nebula, the same physical process that makes our sky appear blue during the day. When starlight encounters small dust grains in a reflection nebula, shorter wavelengths, blue light, scatter more than longer wavelengths, red light, giving the nebula a characteristic blue glow. Dark nebulae are so dense with dust that they block light from stars behind them, appearing as dark patches or silhouettes against the bright background of the Milky Way. The famous Horsehead Nebula in Orion is a dark nebula, its distinctive equine shape silhouetted against a glowing emission nebula behind it. These dark nebulae are cold, temperatures may be only a few degrees above absolute zero, and dense enough that new stars are forming within them. They represent some of the raw material from which future generations of stars and planets will form. Planetary nebulae, despite their name, have nothing to do with planets. Early astronomers using small telescopes thought they looked somewhat like the disks of planets, hence the misleading name. They actually form when sun-like stars shed their outer layers at the end of their lives, creating expanding shells or bubbles of glowing gas around the dying star's hot core. The core, now exposed, is hot enough to emit intense ultraviolet radiation that causes the expelled gas to glow, creating some of the most beautiful and symmetrical structures in space. The Ring Nebula in the constellation Lyra is a beautiful example of a planetary nebula, appearing like a cosmic smoke ring about 1 light-year in diameter. At its center is a white dwarf, the exposed core of the star that created the nebula, now roughly the size of Earth but containing about 60% the mass of the Sun, compressed to incredible density. A teaspoon of white dwarf material would weigh several tons on Earth. This white dwarf is the ultimate fate of our own Sun billions of years from now. Planetary nebulae are relatively short-lived by cosmic standards, lasting perhaps 10,000 to 50,000 years before the gas disperses into the interstellar medium. But in those thousands of years, they represent a beautiful stage in stellar evolution, a star's final artistic expression before fading to a white dwarf that will cool slowly over trillions of years. The Crab Nebula is the remnant of a supernova explosion that was observed by Chinese astronomers in 1054 AD. They described it as a guest star, so bright it was visible during the day for several weeks. The nebula is still expanding outward from that explosion at a speed of about 930 miles per second, and at its center lies a rapidly spinning neutron star called a pulsar, rotating 30 times per second and emitting beams of radiation that sweep across space like a cosmic lighthouse. The Crab pulsar is the collapsed core of the star that exploded. During the supernova, the core collapsed to the point where protons and electrons combined to form neutrons, creating a star made almost entirely of neutrons packed together at nuclear density, a neutron star. A teaspoon of neutron star material would weigh about 1 billion tons. The Crab pulsar is only about 12 miles in diameter but contains more mass than our Sun. It's one of the densest objects in the universe short of a black hole. These nebulae represent both the birth and death of stars, the eternal recycling of matter through the galaxy. Material ejected by dying stars or exploding supernovae mixes with the interstellar medium, enriching it with heavy elements. This enriched material eventually becomes part of new nebulae, which collapse to form new generations of stars and planets. The calcium in your bones might once have been part of a planetary nebula, ejected by a dying star billions of years ago. The iron in your blood might have been forged in a supernova explosion and scattered into space, later incorporated into the molecular cloud that collapsed to form our solar system. Let yourself drift through these colorful clouds, witnessing the eternal cycle of stellar birth and death, creation and transformation that shapes our universe. Imagine floating through the Orion Nebula, surrounded by glowing gas illuminated in shades of red and green, with young stars shining through the mist like beacons. Feel the subtle push of stellar winds, the pressure of light itself, as radiation from nearby stars shapes and sculpts these cosmic clouds. This is where stars are born, where the materials for planets and life are created, where the universe renews itself in an endless cycle that has continued for billions of years and will continue for billions more. The Milky Way, our galactic home. On a clear, dark night, far from city lights, you can see a luminous band stretching across the sky from horizon to horizon, the Milky Way. This misty river of light, this stellar pathway, is actually our view of our own galaxy from within it, seen edge-on as we look through the galactic disk. Ancient peoples around the world created myths to explain this luminous band. In Greek mythology, it was milk spilled from the breast of the goddess Hera. In Chinese astronomy, it was a silver river separating lovers. Native American tribes saw it as a path for spirits. All were looking at the same phenomenon, the combined light of billions of stars in our galaxy, so numerous and distant that they blend together into a continuous glow. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure made of stars, with spiral arms extending from the ends of this bar. It contains between 100 and 400 billion stars. The exact number is uncertain because many stars are hidden by dust, and many are too faint to detect even with our best telescopes. Our solar system is located in one of the spiral arms, the Orion Arm or Orion Spur, about 26,000 light-years from the galactic center, roughly halfway out from the center to the edge. We're in a rather ordinary location, neither in the dense central bulge nor in the sparse outer reaches, but in a region of moderate stellar density where conditions have proven conducive to the development of life. The Milky Way is vast almost beyond comprehension. It measures about 100,000 light-years in diameter, meaning if you could somehow travel at the speed of light, 186,000 miles per second, it would take you 100,000 years to cross from one side to the other. The galaxy is relatively thin compared to its width, only about 1,000 light-years thick in the disk where most stars reside, though there's a central bulge that's much thicker. At the center of our galaxy lies a supermassive black hole called Sagittarius A*, pronounced Sagittarius A star. This black hole has a mass equal to about 4.15 million times the mass of our Sun, yet it occupies a region of space only about 17 times the diameter of the Sun. For decades, astronomers inferred its existence by observing stars near the galactic center orbiting something massive and invisible. These stars move at tremendous speeds, some reaching several % of the speed of light, in tight orbits around the galactic center. The star S2, for example, completes one orbit around Sagittarius A** in only 16 years, traveling at speeds up to 3% the speed of light at its closest approach. In 2022, the Event Horizon Telescope collaboration released the first actual image of Sagittarius A*, or rather, an image of the shadow it casts and the glowing ring of hot material orbiting it. Creating this image required linking radio telescopes around the entire Earth into a virtual telescope the size of our planet, achieving the resolution necessary to photograph something so small and distant. The Milky Way doesn't sit still in space. It rotates, with stars, gas, and dust orbiting the galactic center. The Sun and our solar system orbit at a speed of about 514,000 miles per hour, completing one full orbit every 225 to 250 million years, a period sometimes called a cosmic year or galactic year. Our solar system has completed about 20 to 23 orbits around the galactic center since it formed 4.6 billion years ago. The last time we were in our current position in the galaxy, dinosaurs had not yet appeared on Earth. The Permian-Triassic mass extinction, the worst extinction event in Earth's history, was still 25 million years in the future. Different parts of the galaxy orbit at different speeds. Stars closer to the center orbit faster, while stars farther out orbit more slowly, though not as much more slowly as Newtonian physics would predict based on visible matter alone. This discrepancy, stars in the outer parts of galaxies moving faster than expected, is one of the key pieces of evidence for dark matter, invisible mass that doesn't emit light but exerts gravitational force. The Milky Way isn't alone. It's part of a collection of galaxies called the Local Group, which includes the Andromeda Galaxy M31, the Triangulum Galaxy M33, and about 80 smaller galaxies. These galaxies are all bound together by gravity, orbiting their common center of mass. Most of the Local Group's galaxies are dwarf galaxies, small collections of stars gravitationally bound to larger galaxies like the Milky Way or Andromeda. The Magellanic Clouds, visible from the southern hemisphere, are two irregular dwarf galaxies orbiting the Milky Way, appearing like detached pieces of the Milky Way in the night sky. The Milky Way and the Andromeda Galaxy are the dominant members of the Local Group, and they're actually moving toward each other at about 68 miles per second. In about 4.5 billion years, they will collide and begin to merge, an event that will take hundreds of millions of years to complete. As they approach, tidal forces will distort both galaxies. Eventually they'll pass through each other. Remember, Galaxies are mostly empty space, so actual stellar collisions will be rare, then fall back together and merge, forming a new elliptical galaxy that astronomers have nicknamed Milky Way. What will this collision look like from Earth, if Earth and humanity still exist? At first, over millions of years, Andromeda will grow larger in the night sky. Eventually, it will fill a large portion of the sky, a spectacular spiral visible even in daylight. The sky will be filled with two Milky Ways crossing each other, the combined light of hundreds of billions of stars. New stars will form in great bursts as gas clouds from the two galaxies collide and compress. Eventually, the spiral structures will be disrupted, and the merged galaxy will settle into an elliptical shape, a ball of stars rather than a disk. The night sky will be bright with stars, many more visible than today because the merger will place many stars in closer proximity to the Sun's new position. But individual stars will rarely collide. Space is so vast that even two galaxies can pass through each other with minimal stellar impacts. The Sun and Earth will likely survive this cosmic collision, though they'll be flung into a new orbit in the merged galaxy. Life on Earth at that time, if it still exists, will witness one of the most spectacular astronomical events imaginable, the collision and merger of two giant galaxies, playing out over millions of years in the skies above. The Milky Way has a halo of dark matter surrounding it, an invisible form of matter that we cannot directly observe but whose gravitational effects we can measure. This dark matter halo is much larger than the visible galaxy, extending perhaps 500,000 light-years or more from the galactic center, 5 times the diameter of the visible galaxy. Dark matter makes up about 85% of the matter in the universe, yet it remains one of the greatest mysteries in astronomy. We don't know what dark matter is made of. We can only detect it through its gravitational influence on visible matter and light. Leading theories suggest it's made of exotic particles that interact only through gravity and possibly the weak nuclear force, but not through electromagnetism, which is why they don't emit, absorb, or reflect light. The Milky Way's visible stars represent only about 15% of the galaxy's total mass. Most of the rest is dark matter, with some contribution from black holes, neutron stars, and other dark or faint objects. We're swimming in an ocean of invisible matter, the scaffolding upon which the visible galaxy is built. The oldest stars in the Milky Way are found in globular clusters, dense, spherical collections of hundreds of thousands of stars. These clusters orbit the galaxy in large elliptical paths that take them far above and below the galactic disk. The stars in globular clusters are nearly as old as the universe itself, over 13 billion years old, formed when the galaxy was young and the universe was only a few hundred million years old. These ancient stars contain very few heavy elements. They're made almost entirely of the primordial hydrogen and helium created in the Big Bang, with only trace amounts of heavier elements. They represent the first generation of stars in our galaxy, survivors from an earlier, simpler era of cosmic history. The light we see from the Milky Way on a clear night represents countless individual stars, too numerous and distant for our eyes to distinguish. Each point of light you might resolve, if you could, is the Sun, possibly with its own planets, perhaps even with life looking back at us across the cosmic gulf. Between the stars lie nebulae, clouds of gas and dust, and vast stretches of seemingly empty space that is actually filled with tenuous gas, cosmic rays, and dark matter. The galaxy is teeming with activity, stars being born, stars dying, black holes consuming matter, planets orbiting their suns, and perhaps, on some of those planets, beings like us looking up and wondering about their place in the cosmos. Allow yourself to feel small in the best possible way, small, yes, but part of something unimaginably vast and magnificent. You are a conscious collection of atoms, able to contemplate the galaxy that created you. The atoms in your body were forged in stars elsewhere in this galaxy, dispersed by stellar deaths, and eventually incorporated into our solar system. You are made of the Milky Way. You are the Milky Way experiencing itself. Beyond the Milky Way, the realm of galaxies. Beyond our own Milky Way, space is filled with billions upon billions of other galaxies, each one an island universe containing billions or even trillions of stars, separated from other galaxies by distances measured in millions of light-years. The universe is a vast archipelago of galaxies, scattered through space in patterns that reveal the large-scale structure of the cosmos itself. Galaxies come in several basic shapes, classified by Edwin Hubble in the 1920s. Spiral galaxies like the Milky Way have rotating disks with spiral arms where active star formation occurs, creating the characteristic spiral pattern from the compression of gas and density waves moving through the disk. Elliptical galaxies are more rounded or football-shaped, ranging from nearly spherical to highly elongated. They're generally made of older stars and contain little gas and dust, so new star formation has largely ceased. Irregular galaxies have no particular shape, often distorted by gravitational interactions with other galaxies. And there are also lenticular galaxies, intermediate between spirals and ellipticals, with a disk but no spiral arms. The Andromeda Galaxy, also known as M31, is the most distant object visible to the naked eye from Earth, located about 2.5 million light-years away. When you look at Andromeda, you're seeing light that left that galaxy 2.5 million years ago, when our ancestors were just beginning to use stone tools, when the genus Homo was in its infancy. The light you see crossed 2.5 million light-years of space to enter your eye, photons that have been traveling through the void since long before modern humans existed. Andromeda is a spiral galaxy similar to the Milky Way but somewhat larger, containing perhaps 1 trillion stars compared to our galaxy's few hundred billion. It's visible as a faint, fuzzy patch in the constellation Andromeda, and through binoculars or a small telescope, you can begin to see its true nature as a vast spiral galaxy tilted at an angle to our line of sight. The Hubble Space Telescope's deep-field images have revolutionized our understanding of the universe's galaxy population. The original Hubble Deep Field, taken in 1995, pointed at a patch of sky no larger than a grain of sand held at arm's length, a region that appeared empty to ground-based telescopes. Hubble's exposure revealed thousands of galaxies in that tiny patch of sky. Every fuzzy blob in the image is an entire galaxy containing billions of stars. This implied that similar galaxy densities exist in every direction we look, suggesting the observable universe contains far more galaxies than previously thought. Later, even deeper exposures like the Hubble Ultra Deep Field and the Hubble Extreme Deep Field pushed even farther into space and time. The most distant galaxies in these images are so far away that their light has been traveling through space for over 13 billion years. We see these galaxies as they appeared when the universe was less than 1 billion years old, giving us a window into the early cosmos when galaxies were first forming. These early galaxies look different from nearby galaxies. They're smaller, more irregular, actively forming stars at high rates. We're witnessing galaxy evolution, seeing how galaxies have grown and changed over cosmic time. The universe has evolved, with small galaxies merging to form larger ones, spiral structures developing, and the overall rate of star formation declining as the supply of gas is exhausted or heated to temperatures too high for star formation. The universe contains an estimated 2 trillion galaxies in the observable volume alone. That's 2 trillion galaxies, each one potentially containing hundreds of billions of stars. If you counted one galaxy per second, it would take more than 60,000 years to count them all. And remember, this is just the observable universe, the portion from which light has had time to reach us. The total universe may be far larger, perhaps infinite. Each one of these trillions of galaxies is a vast collection of stars, nebulae, planets, black holes, and dark matter, bound together by gravity and separated from other galaxies by immense distances. Even the nearest major galaxy to us, Andromeda, is 2.5 million light-years away, a gulf so vast that light takes 2.5 million years to cross it. Most galaxies are separated by tens of millions or hundreds of millions of light-years. The space between galaxies is not truly empty, It contains tenuous gas, the occasional wandering star ejected from a galaxy, and presumably dark matter, but it's far emptier than the space within galaxies. Some galaxies are actively forming new stars at a prodigious rate, birthing hundreds or even thousands of stars per year. These starburst galaxies are often the result of galaxy collisions or mergers, which compress gas clouds and trigger intense bursts of star formation. When galaxies collide, the gas clouds within them collide and compress, creating conditions ideal for star formation. The result is a galaxy ablaze with young, hot stars, glowing brilliantly in ultraviolet light. Other galaxies are quiescent, with star formation largely shut down. Elliptical galaxies in particular have exhausted or ejected most of their gas, so new stars can no longer form. They're populated by older, redder stars, red and dead, in astronomical parlance, slowly evolving and fading over billions of years. Many large galaxies like the Milky Way and Andromeda have supermassive black holes at their centers, millions or billions of times the mass of the Sun. In some galaxies, these black holes are actively consuming matter, creating some of the most energetic phenomena in the universe: active galactic nuclei, quasars, and blazars. Material falling into the black hole heats to millions of degrees and emits tremendous amounts of radiation across the electromagnetic spectrum. A quasar can outshine its entire host galaxy, and the most powerful quasars can be seen across the entire observable universe. These were more common in the early universe when gas was more abundant and galaxies were more actively feeding their central black holes. The universe is expanding, and this expansion is accelerating. Edwin Hubble discovered in the 1920s that galaxies are moving away from each other, with more distant galaxies receding faster than nearby ones. This discovery revolutionized our understanding of the cosmos, revealing that the universe had a beginning and has been growing ever since. This expansion means that the universe is constantly growing larger, spreading the galaxies farther apart with each passing moment. It's not that galaxies are moving through space away from each other. Rather, space itself is expanding, carrying galaxies along with it like raisins in rising bread dough. The farther apart two galaxies are, the more space there is between them to expand, which is why more distant galaxies appear to recede faster. In 1998, astronomers made an even more surprising discovery. The expansion of the universe is accelerating. This was completely unexpected. Gravity should be slowing the expansion down, not speeding it up. The force driving this acceleration has been named dark energy, and it represents about 68% of all the energy and matter in the universe, yet we still don't fully understand what it is. Dark energy appears to be a property of space itself, a kind of energy inherent to the vacuum. As the universe expands and more space is created, more dark energy comes into existence, driving further expansion in a runaway process. If dark energy continues to dominate, the universe will expand forever, growing colder and more dilute. In the far future, galaxies will be so far apart that beings living in those distant times will look up and see a much lonelier cosmos, with only their local group of galaxies visible, all other galaxies having receded beyond the cosmic horizon, their light redshifted beyond detection. Eventually, even the galaxies in their local group will have merged into single giant galaxies. Stars will burn out, and no new stars will form once the gas is exhausted. The universe will grow cold and dark, with only occasional flares as stars fall into black holes or dead stars collide. Eventually, even black holes will evaporate through Hawking radiation over timescales of 10 to the power of 100 years or more, leaving the universe as a thin soup of elementary particles growing ever more dilute as space continues to expand. This is sometimes called the heat death of the universe, a state of maximum entropy. But that's trillions upon trillions of years in the future. For now, in our cosmic moment, the universe is still vibrant, filled with galaxies actively forming stars, creating new worlds and perhaps nurturing life and consciousness. Galaxies cluster together in groups and superclusters, forming a cosmic web structure that spans the entire observable universe. If you could view the universe from an impossibly distant vantage point, you would see that galaxies aren't randomly distributed. They're organized into filaments and sheets surrounding vast voids, regions of space with very few galaxies at all. The cosmic web looks somewhat like the structure of a sponge, with galaxies concentrated along the surfaces of bubble-like voids. These structures formed from tiny density variations in the early universe, variations that grew over billions of years under the influence of gravity, particularly the gravity of dark matter. Slightly denser regions attracted more matter, growing denser still, while less dense regions lost matter to their denser neighbors, becoming voids. The result is the cosmic web we see today, a pattern that encodes information about the universe's composition, age, and evolution. Our local group is part of the Virgo supercluster, which contains about 100 galaxy groups and clusters. And the Virgo supercluster is itself part of an even larger structure called the Laniakea supercluster, which contains about 100,000 galaxies. Laniakea means immense heaven in Hawaiian, an appropriate name for a structure that stretches 520 million light-years across. All these galaxies are moving through space together, flowing toward a gravitational anomaly called the Great Attractor, a region of space where mass is concentrated, pulling nearby galaxy clusters toward it. The cosmic web, the distribution of galaxies, dark matter, and voids across the universe, is one of the largest structures we can study. It helps us understand how the universe evolved from the nearly uniform conditions shortly after the Big Bang to the complex, structured cosmos we see today. Cosmic origins and destiny. As we near the end of our journey, take a moment to consider the profound nature of what we've explored. The universe is approximately 13.8 billion years old, born in an event we call the Big Bang. In that time, it has evolved from an incredibly hot, dense state, far hotter than the center of any star, to the vast, cold expanse we observe today filled with galaxies, stars, and planets. Everything we see, everything we are, emerged from that initial expansion. In the beginning, the universe was so hot that atoms couldn't exist. Even atomic nuclei couldn't exist. Everything was a seething plasma of elementary particles. Quarks, electrons, photons, neutrinos, too energetic to combine into anything more complex. As the universe expanded, it cooled. Within the first few seconds, quarks combined to form protons and neutrons. Within the first few minutes, some of these protons and neutrons fused to form the nuclei of helium and trace amounts of lithium. But it was still too hot for electrons to bind to these nuclei to form atoms. The universe remained opaque for the next 380,000 years, filled with a hot plasma where photons constantly scattered off free electrons, unable to travel far. But as the universe continued to expand and cool, eventually it cooled enough for electrons to combine with nuclei to form neutral atoms, mostly hydrogen with some helium. At this point, photons could travel freely for the first time. The universe became transparent. The light released at that moment is what we see today as the cosmic microwave background radiation, redshifted by the expansion of the universe from visible light to microwave wavelengths. The atoms in your body were forged in the hearts of stars. The oxygen you breathe, produced by stars more massive than the sun fusing helium and carbon. The carbon in your cells, created when helium nuclei combined in the cores of dying stars. The calcium in your bones, the iron in your blood, all forged in stellar furnaces through nuclear fusion, then scattered into space when those stars died. When those stars exploded as supernovae or shed their outer layers as planetary nebulae, they enriched the interstellar medium with these heavy elements. When our solar system formed 4.6 billion years ago, it incorporated these elements and they eventually became part of Earth, of life, and of you. The iron in your blood was created in a supernova explosion billions of years ago, forged in the final moments of a massive star's life when its core collapsed and rebounded in a catastrophic explosion. That explosion sent the iron hurtling through space at millions of miles per hour. Eventually, this iron became part of the molecular cloud that collapsed to form our sun and solar system. It was incorporated into Earth's interior, eventually brought to the surface by geological processes, absorbed by plants, consumed by animals, and ultimately became part of you. Every atom of iron in every red blood cell in your body has this cosmic history. We live on a small planet orbiting an average star in one spiral arm of a typical galaxy, which is itself just one of trillions of galaxies in the observable universe. Yet here we are, conscious beings capable of contemplating our place in this cosmic vastness, able to study and appreciate the beauty and complexity of the universe that gave rise to us. We are the universe become conscious, matter examining itself, the cosmos coming to understand its own nature. The great astronomer Carl Sagan once said, "We are a way for the cosmos to know itself." This is not mere poetry, it's a profound truth. The atoms that make up your brain, that enable your thoughts, that allow you to contemplate the universe, were created in stars. You are made of the cosmos, and through you, the cosmos examines itself. Your consciousness is a remarkable emergence, the result of 13.8 billion years of cosmic evolution, from the Big Bang through the formation of galaxies and stars, the synthesis of heavy elements, the formation of our solar system, the development of life on Earth, and the evolution of complex brains capable of abstract thought. The night sky connects us to this larger reality. When we look up at the stars, we're reminded that we're part of something far greater than ourselves, a universe that has been evolving for billions of years and will continue for billions more. We're part of an unbroken chain of cosmic evolution from the Big Bang to this moment, connected to everything that has ever been. And what of the future? What awaits the universe in the billions and trillions of years to come? If dark energy continues to dominate, the universe will expand forever. Stars will continue to form for trillions of years as long as gas remains to fuel them, but eventually the supply of gas will be exhausted. The last stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. The universe will grow dark. Occasionally, white dwarfs might collide, creating brief supernovae that briefly illuminate the darkness, but these will become rarer and rarer. Black holes will slowly evaporate through Hawking radiation, a process so slow that it will take 10 to the power of 100 years or more for even stellar mass black holes to disappear completely, and much longer for supermassive black holes. Eventually, the universe will reach a state of maximum entropy, a state sometimes called heat death. Not because it's hot, but because all energy will be evenly distributed, no longer available to do work. No stars will shine, no energy will flow, and nothing will change. The universe will persist in this state, essentially dead for eternity. But this is so far in the future, trillions upon trillions of years, that it's almost meaningless to contemplate. For now, in our cosmic moment, the universe is alive and vibrant, filled with stars and galaxies, with processes of creation and destruction playing out on every scale. We are fortunate to live in this era when the universe is neither too young, still opaque and featureless, nor too old, cold and dark. We live in the universe's prime, when stars shine brightly, galaxies dance through space, and at least one species of conscious beings can look up and wonder at it all. Closing, return to Earth. As we close this journey, let yourself relax completely. Feel the weight of your body, grounded here on Earth, solid and real, while your mind has traveled through the cosmos, visiting distant worlds, floating among the stars, drifting through nebulae, contemplating galaxies and the structure of the universe itself. Breathe in the vastness of space. Breathe out any tension or worry. Let it dissolve into the cosmic expanse, insignificant against the backdrop of infinity. Imagine yourself floating peacefully among the stars one final time, surrounded by the gentle light of distant suns. You're suspended in the velvet darkness of space, weightless, without up or down, without beginning or end. The Milky Way stretches above and below you, wrapping around you like a luminous river flowing through the darkness. You are immersed in starlight, bathed in the ancient glow of countless suns, each one a nuclear furnace burning steadily, sending photons across space to reach you in this moment. Nebulae glow in the distance like watercolor paintings on the canvas of space, blues, reds, purples, and golds blending together in cosmic artistry. You can see the Orion Nebula, a vast stellar nursery glowing pink and red with the light of ionized hydrogen, young stars shining within its depths. The pillars of creation rise like cosmic monuments, towers of gas and dust where new stars are being born. The Crab Nebula pulses with energy, its central neutron star spinning and sending out beams of radiation. Each nebula is a scene of transformation, matter recycling itself, old stars becoming new. Galaxies spin slowly in the darkness, each one a universe unto itself, containing countless stars and untold possibilities. You can see the graceful spiral arms of the Milky Way curving away from you. In the distance, the Andromeda Galaxy shines, a spiral of stars slowly approaching us through space, destined to merge with our own galaxy billions of years from now. Farther still, countless other galaxies dot the darkness, each one containing billions of stars, each star potentially with planets, each planet a world with its own story. The moon rises over a distant horizon, casting its silver light across alien landscapes you've never seen but can imagine. Perhaps it's a moon of Jupiter with the giant planet filling half the sky, its bands of clouds slowly rotating, the great red spot visible as a vast oval. Or perhaps it's a moon of Saturn with the magnificent rings arcing across the sky, so close you feel you could reach out and touch them. Or a moon orbiting an exoplanet hundreds of light years from Earth, with an alien sun rising in the sky, its color slightly different from our sun, illuminating a world utterly unlike our own. You are part of this cosmos. You are made of stardust, assembled from atoms forged in the cores of long-dead stars. The calcium in your bones was created in a supernova explosion. The oxygen you breathe was produced in the core of a massive star. The hydrogen in your body, most of the atoms in your body actually dates back to the Big Bang itself, formed in the first few minutes of the universe's existence. You are ancient and you are new. You are small and you are infinite. You are the universe experiencing itself, contemplating its own vastness. As you drift towards sleep or simply rest in this peaceful state, know that the stars will continue their eternal dance. The galaxies will keep spinning through space, gravity pulling them along their paths. Nebulae will give birth to new stars and old stars will die, recycling their matter to create new worlds. The universe will go on, vast and magnificent and mysterious, following the laws of physics that have governed it since its beginning. And you are here now in this moment connected to it all. Every breath you take contains atoms that were once part of stars. Every thought in your mind is the result of 13.8 billion years of cosmic evolution. You are not separate from the universe. You are an integral part of it, as much a part of the cosmos as any star or galaxy. Rest well, cosmic traveler. Let yourself sink into deep relaxation or gentle sleep. The stars will still be there when you wake, shining steadily across the light years. The moon will continue its eternal orbit around Earth. The sun will rise tomorrow as it has for billions of years, warming our world with light that began its journey from the solar core long before you were born. The night sky welcomes you home. Not just to Earth, your planetary home, but to the cosmos itself. Your true home, the place where you've always belonged, the universe that created you and of which you are a part. Close your eyes if you haven't already. Feel yourself floating in that infinite space, surrounded by gentle starlight. Feel the rhythm of your breathing, slow and steady. Feel your heartbeat, a rhythm that echoes the pulses of neutron stars, the orbital dance of binary stars, the cosmic rhythms that flow through all of existence. You are safe. You are at peace. You are home. The universe cradles you in its vastness. Rest now. Dream of stars and galaxies, of nebulae and distant worlds, of the infinite possibilities that fill the cosmos. The journey continues even as you rest. The Earth spins beneath you, carrying you through space at thousands of miles per hour. The Earth orbits the Sun. The Sun orbits the galactic center. The Milky Way moves through space. Everything is in motion, everything is connected, everything is part of the cosmic dance. And you are part of it all. Rest well. The stars are waiting. They will always be waiting. Welcome home, starlight. Welcome home.